So let's learn about the inverse hyperbolic functions. Every function that we have learned, we learn the inverse, its inverse or the inverse of its operation. Let's start with sin x. We have learned that sin x it looks like that. And to find its inverse, what is the first thing to check when you need to find the inverse of a function? You check if it is 1-to-1 or not. So we learned that sin x is 1-to-1 or not. It is 1-to-1. So its inverse, it is just that simple. We just say that y is equal to sin inverse x is just the inverse. What is the graph of that inverse function? I just make a reflection about the y equals x, the y equals x line. So that red curve is just the sin inverse x. Okay, so what is sin inverse x? It is the angle which is the hyperbolic angle. It is not an angle in the ordinary fashion, but it is an hyperbolic angle for which has a sin equal to x. Or when I need to solve, for example, I learned this is sin x. For example, this is alpha. This is value. It is just called sin inverse of alpha. Okay, it is the x which corresponding, or the hyperbolic angle which corresponds to a given value x. Okay, so that is sin inverse x, and it is 1-to-1. So that's why the sin inverse x it would look like that. It would look like that. Okay, so that is sin inverse x. It is straightforward. And also would be the case for tanh x. Why? Because tanh x also is 1-to-1. Tanh x had two asymptotes like this, and it was like this, and that was from 1 to -1. Okay, the output for a tanh was always from -1 to 1. In this property, it is much like the sine and cosine before. We learned before that sine and cosine is always inside the interval. The output is inside the interval it is bounded to the values of from -1 to 1. And that is also the case for tanh x. The output of tanh x is always bounded by -1 and 1. Okay? This is a 1-to-1 function, so that's why the inverse will just be straightforward. So what is the inverse function for this one? It will just be graphed like this. Instead of horizontal asymptotes, I will have vertical asymptotes like this, and the inverse function will just be like this. From -1 to 1. From -1 to 1. Like this. This is tanh inverse x. For the graph of tanh inverse x, it looks like a previous function which we learned before. That's the tan x, not the tan x exactly. It is the restricted tan. It is much like the restricted tan, but with different values in the x-axis. Okay. So that is for sin inverse and tanh inverse. Now, what is the domain and range of sin inverse? It is R and R, because we learned that sin x itself has a domain of R and a range of R. What about tanh inverse x? We have learned that we just swap the domain and the range with, or we interchange the domain and range of the function and its inverse. So that's why the domain of tanh inverse will just be from -1 to 1 with open. Okay, so that's why there is a condition for what is inside the tanh inverse. When I give you a problem and I tell you find the domain of tangent inverse of, for example, x squared minus 1. For this case, I will just take x squared minus 1 and I put it inside the interval, the inequality from -1 to 1, and I solve the inequality as if I learned before. It is just the same condition of sine inverse and cosine inverse. We'll just have the same condition for tangent inverse. Okay? What about the range? The range is just R. The range or the output is just R. So it is straightforward for either the sine, the sine, and the tangent. But this is not the case for cosine x. Let's check cosine x. Why? Because cosine x is not a one-to-one function. Not one-to-one. It is an even function, and we learned that any even function is not one-to-one. So what would you do for a not one-to-one function to find an inverse for it? We just make a restriction for the domain. Yes, we choose a restricted domain for cosine x such that it satisfies two conditions. It is one-to-one in that restricted domain, and the other condition that it covers the whole range of the original function. The whole range is this range from 1 to infinity, and it is obvious that choosing that domain in x greater than 0, that part of the function, is just sufficient for us to define the restricted cosine. So what is the restricted cosine? Restricted cosine is graphed like this. It is cosine x with the restricted domain x greater than or equal to 0. So that function with its restricted domain is one-to-one and is covering the whole range. It is covering the whole range from 1 to infinity. Now, if I need to find the inverse of that function, I may make a reflection about y equals x. So in this case, I will have a curve looks just like this. So a curve of cosine inverse x, it starts from 1 like this, and it looks like this. And you may like it that it is just much similar to root of x minus 1, because the sine was much like x squared plus 1. If you look at the inverse of this function, you will find that it is just root of x minus 1, or root x shifted right 1. Root x shifted with a right shift of 1, like this. Okay? It is much like the curve of root x minus 1. Okay? So in this case, the domain will be from 1 to infinity. And that is a condition that you must know. Whenever I give you a problem, I tell you, for example, cosine of 3x minus 1. Find the domain of cosine inverse of 3x minus 1. How would I solve this problem to find the domain? I would just say that 3x minus 1 is greater than or equal to 1. Okay? I just put the condition that what is inside the cosine inverse must be greater than or equal to 1. Then I solve the inequality as usual. What about the range of cosine inverse? What about the range of cosine inverse? It is from 0 to infinity. From 0 to infinity. Okay, cosine inverse is positive, or cosine inverse, it is just positive or 0. And so for the cosine, whenever I give you this value, for example, this one is just the cosine inverse of alpha. And the other x, it is just the negative of that one. So a cosine inverse must have a positive value. A cosine inverse must have a positive value. It is much like the root. Much like the square root. The square root is, when I tell you what is square root of 9, it is only positive 3. There may be another value which is negative 3, has the same squaring, but I just say choose the square root to be with a positive value for the condition of the restricted domain. And that is also the case for a given value of cosine. I will have two values that give me the same cosine, but one of them is called cosine inverse x, which is the positive one. The positive one is called the cosine inverse, and the negative one is called the negative of cosine inverse. Okay? So these are the three inverse. These are the three inverse hyperbolic functions. Now we learn about the inverse hyperbolic functions in order to solve equations. Solve equations in hyperbolic functions. Now, solving any equation may encounter inverse functions. And we learned that the set of solutions are always expressed in terms of the inverse function. The inverse function has just one value, but for a given equation, I may have more than one solution. For example, if I told you that x squared is equal to 4, this is an equation. This is an equation. The inverse of x, the inverse operation of 4, I will say that square root of 4 just has one value, which is 2. Okay? But the set of all solutions of this equation is plus or minus root 4. Root 4 is the inverse function of 4. Okay? Root 4, and it just has one value. But to find the set of all solutions, you will find that all solutions are expressed in terms of the inverse function. We have learned that same concept when we solved trigonometric functions, so trigonometric equations. For example, when I say that sine x equal to some number alpha, we have learned that we have two basic angles, which is sine inverse alpha and pi minus sine inverse alpha. We had these two basic angles, then we added up some multiples of 2 pi and so on. But as you can see, that all solutions are expressed in terms of that inverse function. So that is the use, or that is the benefit of defining inverse function. You make it as the unit for solving equations. All the solutions are expressed in terms of the inverse function. Okay? All the solutions are expressed in the terms of the inverse function. Now let's check different forms for hyperbolic equations. For example, we have three different main forms for hyperbolic equations. Cosine x equal to alpha. As we have studied before, cosine x equal to alpha and sine x equal to alpha and tan x equal to alpha. We have learned the three basic equations in trigonometric equation or trigonometric functions. These were three basic forms from which any other equation may be simplified or may be directed to be expressed in any of these three equations. That's why we will have also three forms of equations for hyperbolic functions, which are, for example, sine x equal to alpha. Sine x equal to alpha. In this case, for hyperbolic functions, we'll find that solving equations is much simpler. Why? Because sine x and cosine and tan x are one-to-one functions. Okay, so I have only one solution. The problem in trigonometric functions that they were not one-to-one, they were periodic functions. So that's why they were not one-to-one, and for a given equation I may have infinite number of solutions. But for this equation I will just have one solution. And this one solution will obviously be the inverse of taking the inverse both sides, which will be sine inverse of alpha. It will just be sine inverse of alpha. So it is just one solution like this. And that is the same case for tan x equal to alpha. What would be solution? The solution will just be tan inverse alpha. So we'll have one solution in both these two cases. But what about this equation? Cosine x equal to alpha. When would the cosine be equal to alpha? Now, this is under the condition that alpha is greater than or equal to 1. Okay? Whenever I have an alpha that is less than 1 or negative, in this case, that equation will be rejected. or it would have no solution. Okay, now what are the solutions for this alpha? We'll have two solutions. One of them is the basic, which is cosine inverse x will be cosine inverse alpha. This is obviously one of the solutions, but there is also another solution, which is this one. What is the other solution? Can I write it in terms of the basic solution, which is cosine inverse alpha? Yes, it is just the negative. So we'll have two solutions for this equation. This is the only equation that have two solutions in hyperbolic functions, which is plus or minus cosine inverse alpha. There is only one case for alpha for which it gives me one solution, which is the case of the zero. If I have this equation, cosine x equals 1, this is solution is, it is plus or minus cosine inverse 1, which is plus or minus 0, which gives me one value, which is 0. So in this case, we will not have plus or minus, it will just give me one value, which is 0. Okay? So there is only one case for which this equation gives me one value, which is when alpha is equal to 1. Now let's solve this equation. Three sine x plus cosine x equal to 0. Now we learned before in trigonometric we will acquire the same skills that we have learned in solving trigonometric functions, in solving trigonometric equations. Okay, we need them to be in the same angle, expressed in terms of the same angle, also in terms of the same function. They are all be expressed in sine, or all expressed in cosine, or all expressed in tan. That is, we have here a similar case. We will just express them in the same hyperbolic angle, and number two, we will just make them expressed as one hyperbolic function. Okay, now for this case I may just rewrite this equation in terms of just one hyperbolic function, which is tan. I may divide by, if I take this one to the negative side, it would be 3 sine x equal to negative cosine x. If I divide by cosine, I will just get 3 tan x will be equal to negative 1, which means that tan x is just equal to negative 1 over 3. Okay? Now for this case, tan x equal to negative 3, this is an ordinary equation. I will just have one solution, which is x is equal to tan inverse of negative 1 over 3. Now remember that tan inverse is the inverse of an odd function, and we learned that the inverse of an odd function is always an odd function. So that's why that negative must be taken out to be tan inverse of 1 over 3. So we just have one solution, which is tan inverse 1 over 3. Now let's check this equation. Sine squared x minus 3 cosine x plus 3 equal to 0. We have just learned the skills that we need to express them in terms of one. First, the same angle. Yes, we have the same hyperbolic angle. Okay. The second condition is to make them in terms of just one hyperbolic function. We need to write it all of them in terms of cosine, or write them in terms of sine. What is most suitable here? to replace the sine squared with cosine, or to replace the cosine with sine squared with sine? Yes, that one, because I have a direct rule for this, that sine squared, it is just cosine squared x minus 1. Now look, I didn't have a confusion in this case. I just know that cosine is the greatest of the hyperbolic functions. That's why I subtracted a 1 from cosine squared to get the sine squared. Okay? If I have in mind the known rule that the cosine is the greatest among all the hyperbolic functions, I will just write the rules easily, like just as if I did in this case. So cosine is greater than the sine, it will be cosine, I just subtract 1 to get the sine squared. So this is minus 3 cosine x plus 3 equal to 0. If I continue simplifying this expression, I will just get cosine squared x minus 3 cosine x plus 2 equal to 0. This may be factorized as this, cosine x, 2 and 1, negative, negative. So that means that we have two equations, that cosine x equal to 2 or cosine x equal to 1. And we learned that for the equation for which cosine is equal to some number, if that number is greater or equal to 1, I will have two solutions. Okay? So x will be just plus or minus cosine inverse 2. X will just be plus or minus cosine inverse 2 for this equation. What about this equation? X will be equal to what is cosine inverse 1? It is, what gives me 1? It is x equal to 0. So that will have only one solution, which is 0. So that's why we have three solutions in this case, which is 0 and plus or minus cosine inverse 2. 0 and plus or minus cosine inverse 2. Okay? Now what about this equation? 8 sine x minus 4 cosine x equals 1. Now, if I had this equation, this similar equation, but for trigonometric functions, that would be a difficult equation for trigonometric functions. For if I had 8 sine x, for example, minus 4 cosine x equal to 1, that equation, if it is solved in terms of trigonometric functions, we will need to put roots. We will just need to put root of 1 minus cosine squared, and that root will be just plus or minus. So we need to square, and we need to check the angles in which quadrant, and so on. So that equation will just be a cumbersome equation or a difficult equation for us to solve. But in hyperbolic function, a similar form, which is exactly like this, it can be easily solved. This equation can be easily solved. Instead of using the standard 3 known forms of hyperbolic equations, which were these 3 basic equations, 1, 2, and 3, no, in this case, I will use the basic definition of the sine and cosine in terms of the exponential. Why? Because this type of equation I cannot convert it to an equation with only one function. It would be difficult for us to express it in terms of only one function by expressing it all as cosine or as cosine or all as sine and so on. It would be difficult for us for this equation without introducing roots. Any trial to put it in terms of one hyperbolic function, it will include roots. Okay? So, and this is not preferable to do that. But we have an alternative. For any of the hyperbolic equations, we have an alternative. What is that alternative? Is to express the equation in terms of the exponentials, which is the basic definition of the cosine and sine. So that's why for this equation I will just write it as 8 times e power x minus e minus x over 2 minus 4 e power x plus e power minus x over 2 equal to 1. Then I make some simplifications. and expand it, so I will get, after some amplification, I will just get that equation. 2e power x minus 6e power negative x equal to 1. Okay, I'll just get that equation. Now, how would we solve this equation? Now, remember that this is e power negative x. This is e power negative x. It is just 1 over e power x. So what step would you expect in this case? I will just multiply the equation by e power x. I will just multiply the equation by e power x to get rid of that negative exponent. So that's why the equation will just convert to 2e power x all squared minus e power x minus 6 equal to 0. I will just written it as a quadratic equation, but in terms of e power x instead of x. This is an ordinary quadratic equation. Which may be solved as e power x to be equal to negative b, or it will be plus 1 plus or minus square root of b squared, which is 1 minus 4a times c, which is negative 6, so that will be like this, all over 2a, which is 4. Okay, so in this case we'll have two solutions, which are 1 plus or minus root 7. No, it is just exactly 7 over 4, which gives me two values, which is 2 and negative 6 over 4. Now, would any of these be rejected? Would any of these two values be rejected? I need to solve two equations. This is e power x equal to 2 and e power x equal to negative 6 over 4. Would any of these two equations be rejected? Yes, the second one must be rejected. Why? We have learned that an exponential is never negative. Even if you try to take len both sides, you know that len of negative is not defined. You cannot find the len of a negative. Okay, so that's why this equation is rejected. But this one is accepted, so it would be x would be equal to len 2. X would be equal to len 2. So that is the solution of this equation. We have learned before to make simplifications to expressions with inverse trigonometric functions. We'll learn also to make simplifications for inverse hyperbolic functions. For example, if you had this example and we need to simplify this expression tan of sine inverse x, how would we simplify this expression? We learned before in trigonometric function we use the same concepts or the same tools that we have used before. In trigonometric functions, we learned before in trigonometric functions, when we find the inverse trigonometric inside the trigonometric function, we name it as denote it as with a variable. For example, alpha. We say alpha, for example, is sine inverse x. Okay, which means that sine alpha is equal to x. In trigonometric functions, we learn to make that triangle for this expression. This is the angle, and we write sine alpha to be x. In this case, we'll make a fake triangle instead of the ordinary triangle. We make the fake triangle for this alpha, which would be sine will be equal to x over 1, and we complete the fake triangle. We're going to complete the fake triangle, treating the adjacent side as the largest side of them, which means that side would be 1 plus x squared under the root. Okay, so that's why whenever I have that triangle or the fake triangle in this case of this alpha, I can find the hyperbolic function of any hyperbolic function that I will need. If I need in this expression, I need to find tanh of alpha. I may ask for any other hyperbolic function. I may ask for finding the sesh or cotangent or any of this. All of this I can find from the fake triangle. Tanh alpha, it is obvious from the fake triangle I have here. It is just would be the opposite divided by the adjacent, which would be x over root 1 plus x squared. So that would be the result of that simplification. This expression is just simplified to be root of 1 plus x over root 1 of x squared. In your calculator, first, how would you use sine and cosine and tanh in calculator? In calculator, you will find a button that is called hype. When you press that button hype, okay, then you press sine, for example, it will just write shine. If you press the button hype before the button sine, for example, it is just equivalent to shine. This is equivalent to shine, and so on. For the inverse functions, you may need to find. You may find in the calculator sine inverse and cosine inverse and tanh inverse. You will find these three functions. You will find them in the calculator by using hype and the inverse. But you will not find, for example, cotangent or cosesh inverse or sesh inverse or cotangent inverse. You will never find these three. You will only find this here. But what if I need to, for example, to calculate? What if I need to calculate? What if I need to calculate sesh inverse of half, for example? How would I calculate this value? We have just as we have learned in trigonometric functions, inverse trigonometric function, that this is exactly cosine inverse of the reciprocal of what is inside the sesh inverse. So that will be just 2. And as a general rule, sesh inverse of 1 over something, it is just the cosine inverse of that term, and so on. If I need, or I may write it like this. Sine inverse of something, it is just cosine inverse of 1 over that something. If I had cosesh inverse something, it is just sine inverse of the reciprocal, and so on. For cotangent inverse something, it is just tanh inverse of the reciprocal. So in that way, whenever I need to calculate this value, I just re-express it, but in terms of the three basic inverse functions, which are sine inverse, cosine inverse, and tanh inverse, by using these three laws. Okay? By using these three laws. Remember, a common mistake, for example, to say that cotangent inverse alpha, for example, or cotangent inverse something, it is 1 over tanh inverse. No, this is a wrong statement. Okay? And in MCQ, you may find it inside the choices. So don't make that mistake. This is not a correct answer for our case. Okay? Now, just for your information, as for the sine and cosine and tanh were exponential functions, their main definition was in terms of exponential functions. We would expect that the inverse of these functions would be expressed in terms of ln. Okay? Just because the sine and cosine and tanh are basically defined as exponential functions. So their inverse will just be expressed by the inverse of the exponential, which is just the ln. And that's why we have three expressions for sine inverse, cosine inverse, and tangent inverse, which are ln of x plus root x squared plus 1, ln x plus root x squared minus 1, and ln over half ln x 1 plus x over 1 minus x. Okay? And remember that the domain of tangent inverse, it is just x from -1 to 1. Okay? So these three rules, you may use these three rules instead of using instead of treating sine inverse as it is, we may rewrite it as ln in these expressions. Okay, so these three expressions are known. How are these expressions derived? How were they derived? It is just a simple idea. For example, if I need to find the expression for tangent inverse x, how would I find this expression? It is easy. Let's say that y is tangent inverse x. So that means that tangent y is just equal to x. But from the basic definition of tangent, I may rewrite it as e power 2y minus 1 over 2y plus 1. I've just chosen that form of tangent just for convenience. So that will be x. Now I may use the cross to be e power 2y minus 1 will just be equal to x e power 2y plus x. Then I need to find y again. I need to solve for y again. So that's why I take that to the other side. So that will be 1 minus x e power 2y. And I take the 1 to the other side. It will just be 1 plus x. So e power 2y, it is just 1 plus x over 1 minus x. So that's why 2y is just equal to the ln. I need to get rid of that e by operating with the inverse of e, which is ln. So that will be 1 plus x over 1 minus x. And that's why y will just be half ln of 1 plus x over 1 minus x. So that is just that y, which is tangent inverse x. It is now expressed in this way by the ln. So whatever was the inverse function, I may use the same procedure, the same idea to express it as y. Then you put it in terms of the exponential. Then you solve again for y. You'll just get any of these three expressions. Okay? So this is the lecture about the hyperbolic functions and inverse hyperbolic functions.